run events for you guys to do comp sci stuff that you're not necessarily getting in classes or other things that you just want to see. So I'm here today because I'm advertising. We have an event this Wednesday, and so everyone at this point has turned in a project to the computer science department, yeah? And everyone has probably turned in a project and then not gotten it back for like 3 or 4 weeks and not had very much feedback on it and have been upset with that. Yeah, so that's a problem, and we're trying to solve it. The faculty has had a bunch of good conversations about how to solve it, but now they want student input. So this Wednesday, if you come to Halligan 111A during the open block, we're going to do a workshop on grading. Specifically, we're going to be talking about what do you think is important to grade, what do you want people to assess you on, and potentially, how do you think we can do that? So the details are there. It's on Wednesday. If you want to come to more events of ours, our Facebook page is there. Next week, Ben Shapiro is going to come talk about his research, and then we're going to have a social the week after that. So we'd love to see you at all of those. Yeah, so I'll see you at noon on Wednesday.
Anybody have any questions for Marcella? Oh, sorry. Clap all you want. Anyone have any questions for Marcella? OK, thank you.
Thank you.
Thanks, Marcella. OK. So I'll leave that on the board, copy it down. And exactly as Marcella said, look, we're looking for better ways to grade you. Like this last assignment took us a little while to get it graded, and I don't like doing that at all, right? I like to get the feedback to you as soon as possible. That also gives you a chance to kind of use the feedback for the next assignment if it was good feedback. So hopefully we'll be able to do that a little better going forward. And since most of you guys are relatively early in your Tufts career, maybe you'll see the fruits of those labors a little later in your Tufts career, if not this year. All right, so before I even start, the homework was due last night. If you, for some reason, still have not submitted it and have some reason why you didn't submit it, oh no, I spent 7 hours until 4 this morning trying to debug this one thing in my quicksort, email me about it. Okay, don't just say I'm just going to submit bad work or whatever. We'll deal with those issues as we get to it. A number of people I was talking to last night were finding, over the last few days, were finding that their quicksort implementation was actually not so quick, right? And I'm trying to figure out why that's the case. There are a whole number of reasons why that's the case. One of them might actually be that the recursive part of the algorithm, remember recursion is expensive in time because you have to save all the state and call another function and so forth. And when you do a recursive function, if you're doing it for really small arrays, well, you're going to have lots and lots and lots of recursion. And that may actually overwhelm the benefits you get from doing a quicksort. Well, how do you do it? Well, a number of people have realized that if you do quicksort and you end up having values that are, or array, when you get to a size array that's very small, then stick it into another algorithm like insertion sort, which is going to be fast and in place. Then you can actually speed up your algorithm. So don't worry about the fact that your quicksort or some other sorts were necessarily slower. And there are some other, optimizations you could have done that would make them faster. But don't worry about that part of it, because we're not actually grading on length of time it takes for your sorts to work. We're grading more on, did you do the right algorithms? Can you document them, et cetera? Okay. So, and did they work? Obviously, if it doesn't sort, then, well, you'll lose some points. But from the standpoint of time, I'm not going to worry about that. Questions on that? No? How'd it go? How many people did find their quicksort, if they did quicksort, was like too slow? Yeah, a number of people. Yeah, that was definitely an issue. People who did radix sort, did you find that one was also slow? Raise your hand. Yeah, a couple other people did that, found that was slow. Same ideas. There's trade-offs to how you're actually implementing it as to whether or not it's going to be faster or slower than what you might expect. But it seems like people worked pretty hard on it, and good job there. We'll have our final assignment of the year is actually going to be on Wednesday. We're going to push it out on Wednesday, and I think you'll find it's kind of fun. It's about searching a list of songs for lyrics. So if you hear a lyric on the radio and go, what song is that? And you can push it into your own little search algorithm, and it will pop out what songs that it knows. Okay? And we'll go from there on Wednesday. Okay, other questions on that? We're going to try, oh, last comment on this assignment. We're going to, this for the sorting assignment. I think what we're actually going to do is the in-person grading this time. So this is going to be your chance to say, to sit with the TAs while they're grading your assignment, and they'll be able to ask you, what were you doing? Why did you make this choice? Or what choices did you make in your algorithm? And look at the actual code. So you'll get feedback right then. It just, the problem with this is just going to be scheduling all of you to meet with TAs at the right time, but we'll figure that out. So we're going to give that a shot for this assignment and see how that goes, and hopefully you'll be a little more satisfied with your grading experience for that one. Okay? All right. Other questions? Great. So we're starting off today, or we're continuing our hashing discussion. And hint, hint, hashing may be important should you decide to use it for the next assignment, just so you know. And by the way, what we're going to talk about for the next 20 minutes or so, 25 minutes, is going to be specifically for today's lab on hashing as well, and tomorrow's lab on hashing. Okay? So here's the overall schedule for today. We're going to do a tip of the day called piping with the little pipe character. Right? It's if you do shift and then backslash, that's the actual character that you get, and it looks like a vertical pipe. And we'll talk about what that is all about. Then we're going to go into some more on hashing. We're going to talk about different strategies for collisions. Okay? Different strategies for how to deal with hash collisions, because as we saw, you can't find a hash algorithm that doesn't collide except in very specific situations, which we'll also talk about. And it means that you're going to have to deal with collisions at some point if you're building a hash table. There's just no two ways about it. You can't say, well, I've got such a big table that I'm not going to have, I'm never going to have collisions. The birthday problem is the reason that doesn't, that isn't a statement you want to be making. Okay? Then we'll talk a little bit about a load factor in terms of what that means for some of these collision algorithms. Then we'll mention perfect hashing algorithms, which we've already seen one, actually, as it turns out. And then we'll go into this other topic, which actually is a completely, could be a whole class on itself, and it's this idea of cryptography, or encrypting messages in some form or another. And we'll talk about what cryptographic hashing in particular means. Okay? And then finally, I mentioned this the other day. I said, should hash functions ever be slow? And we'll talk a little bit about that. Okay? All right. Let's go into the Unix tip of the day, piping with the little pipe character, the vertical line character. So Unix, I don't know if you guys know, Unix has been around since the mid-70s. And it was designed at Bell Laboratories, which was the research arm of AT&T at that point, and one of the best research labs in the world. Unfortunately, with the changes in AT&T, it's probably not as prominent these days. But they designed Unix, and along with some other groups as well. But they basically designed Unix. And one of the killer features of Unix was this idea of piping commands. Okay? And what it allows you to do is allows programs to be modular. And you know how we're always saying, break up your functions, and we have that rule that says your functions can't be more than 31 lines, and you guys end up scrunching them together to try to do that? Well, a better idea is to make them modular. In other words, your function should do one thing. Well, Unix took this to the extreme in terms of your program should do one thing, and do one thing well. Right? So you shouldn't have necessarily a program that does a whole bunch of manipulations on some text and has the ability to sort through it, because that just adds a layer of complexity. Why not build another whole program that just does sorting and have the ability to say one program goes and gets pushed into another program, the output of one becomes the input of the other, and then they're each relatively small and relatively easy to comprehend. And that's what Unix, that's one of Unix's killer features. Okay? And here's how it actually works. We've already seen the greater than and less than used to pipe. And what we mean by pipe is think of a pipe and think of putting one thing in one end of the pipe and then out the other. The greater than and less than is used to input information from files and output information to files, output text to files. Right? And that's what those ones are for. Well, if you want somewhere in the middle of those two things to actually have the output of a program go to the input of another program, you can't use that directly. Okay? What you do instead is you use this piping character, and the programs themselves, the way Unix is built, they actually both run at the same time. It's not like you're doing a whole chunk of one and then a whole chunk of the other. The way it's written is you're doing, like, as one is outputting, the other one's inputting, and they're running kind of in parallel, which also tends to speed things up. So that's kind of neat too. Okay? But that's how it actually works. Here's what you actually do, or here's some examples of the piping. Let's say you wanted to list all the files. List-A1. In fact, I'll show you that right here. ls-a1. Okay? In fact, what I'm going to do is make sure my doc is hidden. There we go. So I've listed all the files here, right? And notice it lists these two little guys too. This means the current directory, and this means the parent directory. Okay? And then I've got all these other files in here. Okay? Well, I can use this idea of piping to say get rid of some of those extra ones. So I just want to know the number of files in my directory, not the parent, not the current one, right? I can do ls-al, and then there's a tail function. And the tail function says, give me just the last lines of a file, and one of the flags is -n plus the number you want to start on. So if I do ls-a1 and then pipe it through tail and do -n plus 3, right? Same thing, ls-a1, and then pipe it through tail-n plus 3. What it does is it just says, give me the last number without the little period and period 1 there. Okay, so this just lists all the files without those other ones. And I've just piped it through. Okay, what if you want to count all the files? So you want to know how many files are in your directory, right? Well, ls probably has a command to do that, but if it, let's say it doesn't, okay, you can do the same thing. You can pipe the output from ls through tail and then through this other program which does one thing and does one thing well. It counts the number of words. It actually counts the letters, characters, and words. In a file, -l means count the letters, right? And so you can pipe the output of that through here, and then it will count the number of lines. I'm sorry, L is lines. Counts the number of lines, characters, and words. And if we further pipe it through WC-L, you end up getting 22. And that's how many files you have. So we've just, using modularity, right, we've been able to, where is it here? There we go. We've been able to say this does one thing well, lists the files. This does one thing well, gives you the last number of lines in your file. And then this one gives you the word count of that. Okay? And you can string these together as long as you want. Okay? And there's actually some good videos of one of the creators of Unix, a guy named Ken Thompson, who actually shows you how to use this. Kind of, it's back from the 70s. It's a great little like old-timey video, right? And it shows you how he uses this to get his work done back then. You just have files and you're just piping them through various things, and you end up with the output that you want. Okay, questions on that? Yes?
In this specific case, what would happen if you use the double ampersand instead of the pipe?
Good question. If you use the double ampersand, okay, this would list all the files, and then it would end, and then the next command would go and wait for input. It wouldn't actually have the output go into the other program. That's what you do here. So that's the difference there. The double ampersand says run one. If it turns out OK, run the other one, and then run the next one. So yeah, that's the difference there. Other questions? Yeah, Peter. Yeah, the greater than or less than are specifically for what we call file descriptors. So files. Anything that takes a file as output, you can use the greater than, right? Greater than. Right? So and the other, if you don't have that, you could do this. You could dispense with this by saying ls-a1 greater than temp file, and then temp file less than tail-n3 output temp2. And then so you could string it together that way, but then you need to create the temporary files in the middle of it, right? Unix actually doesn't have, the cool thing about it is because it's running in parallel, it doesn't actually need any temporary output files in general, unless memory is so huge. In general, it doesn't need them at all. Yeah. Other questions on that one? Kind of a neat little function, a neat little idea. And again, one of the killer functions of Unix, to be able to do that. All right. So last week I showed you a hashing program, like a couple of them, right? I showed you one in Scheme, which most of you guys hadn't seen, and then the Comp 50 people were like, yay, Scheme. And then I showed you one in C++, and you could write these little things in any one. The one I forgot to show you is the one in lolcat. there's a programming language somebody's actually created called lolcat speak, right? Like ICANN has cheeseburger or whatever, right? So yeah. So you end loops with like K thanks and I has a word dictionary, right? Kind of funny that you end the whole program by saying K thanks bye, right? You start it with hi, right? So it's actually a legitimate programming language. I don't know how well defined the compiler is at this point, but it's in there. So anyway, and notice everything's capitals, of course it is, right? You have to do capitals. Anyway, so yeah, and this was the definition of that table, the hash code table that we came up with. All right. So last week, and sorry about this linked list looks all broken. This is a linked list. Before it was on the whole thing, and I wanted to have the board available, so I just kind of tried to squish it in. This is just basically, if this is your hash table, anywhere you hash a word, and it goes into some bucket, right? And you do the modulus on it to make sure it fits in your buckets. You hash the code, and it goes into some bucket. If the bucket is empty, you put the value there, right? Or you have a scheme like this, or you have a linked list here that you start adding onto. Okay, so if two elements collide, then in this situation we call chaining. Okay, if they collide in chaining, and when you're chaining, you just simply say, fine, it's going to go in this bucket, and then I'm going to create another linked list, or a linked list that's going to add it on. Okay. Question: well, first of all, if you are inserting into the hash table, where do you want to actually add your next chain? At the beginning or at the end? What's a good idea? It's somewhat arbitrary, but just so you can think about it, where's a good place to add that next link? At the beginning or at the end? Why first? And somebody else said end. What? Speed. At first would be faster speed. OK, well, what were you saying? Beginning. Oh, OK. Yeah, if you put it at the beginning, there's a couple different things. So first of all, you can insert into a linked list at the beginning very easily, right? You guys all know how to do that, right? Otherwise, you'd have to look through all of them and then get to the end. Now, there are cases where you're going to want to look through in order so you don't like put two of the same value in there, like two of the same key into there. So that's a different idea. But the other one is, in some cases, let's say you're putting values into your hash table. Well, there might be some cases where you're going to read back those values you just put in sooner as well. So again, it comes down to, and maybe not. Maybe it's, oh, I'm going to put a bunch of values in, and then it turns out I'm going to read them in reverse order or something. Well, then you might want to think about how you're inserting them into there. But it all degrades down into the idea of you got to make your choices based on what your use case is, right? So it all comes, and it also degrades the idea of what's a linked list in the end, and what are the trade-offs with linked lists, adding at the beginning or at the end. Okay. So anyway, you do that. If it's empty, you have something that says it's a null node or whatever that says, hey, this is empty. Okay. But the nice thing about this is, what can you tell me if I wanted to add 1 billion elements to this 1, 2, 3, 4, 5, 6, 7 element array? If I wanted to add 1 billion characters to this, what's nice about this structure? Anything? It'll be slow. But what is good about it? Yeah? The size of the array is not going to change. Right. You can always fit every one of your values into this array. So you pick a big enough array, and if you know something about your data set, you pick a big enough array to begin with, this chaining is not going to be too bad. And remember, we want our load factor to be relatively close to 1, maybe a little bit less than 1, so that the number of buckets are like just about the same size as the number of elements we're expecting. Okay, that's probably a good choice. Maybe a little bit bigger. And in that case, you'll generally, if you have a good hash function, not have too many collisions. And you'll be able to have relatively short chains, and you'll still get constant lookup. Okay? So that's chaining. Okay? Let's see. Linked list adds the elements in the hash to collide. You have to search. So the only other issue here is that you do have to have this other data structure, right? You have to have a linked list that you're going to deal with. And your structure kind of goes this way in an array, and then this way with linked lists. And it can get a little bit complicated, right? Not too bad, especially if you have good structures that you're going to be adding into. It's not bad. But it does complicate it just a little bit in that sense. Okay? All right. there are alternatives. So let's think about what some of the ideas might be. Let's see if we can come up with a couple of alternatives to this. Let's say we have to hash, and it comes out to be in this location right here. Okay? And the next available location is actually here. Okay? And it's got some other empty spaces and other filled spaces here. What are some ideas about how we might go ahead and not have any, let's say we're not allowed to add anything but values into these buckets. Like you can't have a change structure now. What other things could we do? Any ideas? Yeah, Marcus?
You could use the same technique for the binary search trees and have some formula for finding the children.
You could have, oh, that's an interesting idea. You could use the same idea as binary search trees and say, where's the child? It's n plus 2 or whatever. That's not a bad idea. Yep, that's actually a good idea. And then what happens if, so what happens like this left child is this one. Then what can you do? What would it be if, what would happen if you looked at the left child and it was filled? You look for the right child, and then you keep walking down this whole tree. That might be a little tricky in that you have to, well, it wouldn't be too bad. I mean, you look at this one's children, then you look at this one's children, etc. Not a bad idea. Okay, not a bad idea. I like that. That might be one of the ways we're talking about. Although I hadn't actually prepared that specifically. I like that though. Yeah.
It has another function which has another image.
Another function which has another image, another array, you mean?
I mean
Or another location?
the domain image of the function. So when you so it's like a hash table, and every element, there's another function to calculate a new location.
There you go. Another function to calculate the new thing. That is actually kind of similar to what Marcus is talking about in the sense that we've got two functions here we're going to deal with. And by the way, Marcus, I'm just thinking, what if you try to fill it at the end here? Well, there is no child at the end of this one. Let's say this was the end of your bucket. You'd no child, but you would wrap around, and then wrapping around, you might end up traversing into the same buckets too often, and then do it. But good idea altogether. But yeah, that's not a bad idea. Where you kind of say, okay, if I collide, let's use a different function. Try this other function and see if that makes sense to put it there. Very good idea. Okay, good idea. How about something even simpler? Like you guys are thinking all these like great grand ideas. If it's not here, where should I try to put it? Next to it. If it's not there, where do I put it? Next to it, right? That's actually the simplest. That's called linear searching, okay? Or like this. So you say, we can check the neighbor and see if it's filled, right? And then finally just keep checking the neighbors until we do that, okay? This is called linear probing. Okay, that's the way this works. And this is what the idea that we're trying to do here is to find what we call an open addressing solution. In other words, and it's kind of a weird name for it, but open addressing means you don't have to change the length of your array. Okay? It means that you don't have to have other structures inside your array. In fact, we don't have to change the length of the array in general for this either, because if this one's filled and this one's filled, well, let's say we started here and we go filled. No, let's say we started here, filled. Well, if we wrap around using that modulus, then we'll still be able to eventually find one here. This does break down at what point? When it's all filled. Right? Because then it'll keep checking neighbors until it finds all the neighbors. And unless you have some check to say, oh, I've checked everybody, then you break. Right? Because then there's nowhere to fill, and it just keeps looping forever because it can't find an actual entry. But at that point, you increase the name of the size of the table and go from there, which we'll talk about as well. This is called linear probing. This works fairly well, except in the cases when you have lots of groupings of hashes, right? So if you end up with a table that has lots of hashes that are grouped together, well, then all the time you're going to end up, let's say lots of times you've hashed this one area of the table, well, then you end up having to look through a whole bunch. So that's not necessarily the best, but it's very simple. It's like dead easy, right? To create that, very easy. And if you do have a good random function, you'll end up doing OK with this. Yeah?
What would happen if you were to put say you put something with the linear probing into a new slot, and then you have something that actually goes in there? How do you deal with that?
OK, so let me see if I get this right. So let's say this one ends up going here because that's where we want to put it. OK, and then you have another one that goes into that slot. It's filled, so you have to do a linear probe starting there on the next. That's how you deal with it. Once it's filled, it's filled. Now, what it ends up being, the interesting part is that you do have to, depending on how many elements are in your table, you do end up with the hash not necessarily pointing to the location. Like in many cases, depending on how many collisions you have, it's not going to point. You're going to have to do this search fairly often, right? But again, the good news is it's pretty easy to do, and you don't have to have an extra structure in here, right? You're just going to keep filling the table until it's filled. Then you have to deal with what to do after that. Yeah, Rose. What to do? Yeah, let's get to how you look for it. That's actually the next slide, I believe. To search for an element, OK, what do? You hash it into that element, and you check the key. So again, we're going to have to keep the keys along with our values, right? So you keep the key. You hash that value, and you say, is there a value here? If there isn't, then you know that there's no, like your value is not in the hash table. So you haven't found it. If there is a value there, check it against the key. If it's not the right key, do your linear search algorithm, right? And then check the next key. And then check the next key. So in this case, we're checking key 3. And we check key 3, and it hashes to here. It's not that one. We have to check the next one. We have to check the next one. So it's just it's a linear search in that case. OK? And if you do find an empty spot, then you say, oh, OK, our key does not exist in the table. If your linear search produces an empty slot, you say, oh, too late. I'm not in my key that I'm looking for is not in the array. OK? Other questions on that? All right. So we can also do another type of probe. The linear one doesn't work so well if you've got groupings of hashes that are right next to each other. Well, another type of probe is do what we call a quadratic probe. OK? And a quadratic probe is also basically the same idea. But what you're doing here is you're saying, OK, hash the code and then add some quadratic based on the number of times you've actually had to look. So the first time you look, this is just going to be 0. And it's going to be 0, whatever your polynomial is. In this case, our polynomial is the attempt we're making, starting at 0, squared. OK, so the 0th attempt, we'll call it, which really is the first attempt, but the 0th attempt, you do the hash code, you add it to the polynomial, which is 0, and you see if it's there. In this case, it's filled, right? Then you do the same thing again, except now the attempt is going to be 1, and you're going to do hash code plus 1 squared. Right? And in this case, it happens to be linear because of the hash function, the quadratic function I chose. But you do this, oh, it's also filled, right? Well, then you check hash code plus 2 squared, because now you're going to be on the third attempt, or 2 in this case. And you're going to jump over some other ones, which might be filled. And if you're grouping, you're going to jump in big chunks. OK? And then you'll end up over here, and you'll put it right there. But same exact idea. To search for it, just make sure you're using the little quadratic probe to do that, to look for it. OK? Questions on that? There are papers and papers dedicated onto the best quadratic function to do for probing based on your hash function. It's just like anything else. People have looked into this, and they have, hey, this is the best quadratic function you can use. You don't want to use one that's too big or it takes longer. And remember, hashing is partially about the fact that its lookup is very fast, but also partially the fact that hashing is very fast. And the bigger your function is, the more detailed your function is, you're going to have a trade-off between that and the number of the amount of time that you've got that you want to use your hash function in. OK? All right, so that's quadratic probing. The lab today mentions quadratic probing, but you don't actually have to use quadratic probing. OK, so there's another one that Remy and Marcus kind of came up with here, right? You can use a second hash function. OK, and you try to pick these hash functions so that if you're in one location, then the hash will jump you to hopefully another somewhat random location. And what you do is you say, same idea as before. The attempt that you have times a completely new hash function on the original value. And that will bump you to some other, hopefully random location. And in that case, you've got a value that is not filled. Okay? And if you pick them judiciously, you'll end up with fewer overall collisions. Okay? Same thing, still open addressing, meaning we don't have to actually do any other structures in here. Right? We're going to fill the table complete. Well, this is the tricky part here is going to be what? Well, not necessarily space, but picking a function that doesn't what? Have more collisions, especially colliding with something you've already collided with. Then you're in bad trouble. All right? So let's say your first function puts it here, and the second one puts it here, and then the third time you do it, it puts it back here. Uh-oh. Right? Then you haven't even checked these other ones. Okay? And that could be a problem. So picking the other hash code, the second hash code takes a little bit of thinking so that you don't actually hash into a location that you've already been. You don't redo a hash before you check all the others. I don't even know if that's possible in some cases. It's like sometimes, depending on where you go, you might not be able to, in many cases, in fact, you might not be able to always have it go to locations that haven't been met yet. Okay? But the idea is still relatively sound in that it's a whole other hash code. Okay? And this is called double hashing. What are you doing? You're hashing the function twice to find a good location for it. Okay? Questions on that one? Awesome. OK, so those are the three things for the lab today that you're going to have to be writing functions for. Linear probe, which is relatively straightforward. Double hashing, which means you're going to add this other hash in here. And then you will have to do a chaining one as well. Okay? The difference is that the chaining one is going to have linked lists in here, so it's a slightly different method. But I think the description's relatively straightforward, and the lab leaders will hopefully walk you through those again and walk you through some of the code in that case. Okay. All right. Questions on open addressing? These other kinds of methods of open addressing. We still haven't figured out how to actually make the table larger, which is kind of an issue. Okay. Let's see. Double hashing, second hash function, repeat the hashing, minimized. Yeah. You also, because you're using the same data for the original or for the second hash, if it's a good hash function, it will actually find a better location because it's based on the original data. Okay. All right. All right. Here we go. Table becomes full. What are you going to do? Right? The algorithm can actually fail to terminate, which would be bad. Right, if you haven't accounted for this. If everybody's filled or your function actually doesn't check all the elements, then you've got a little bit of a problem. You need to keep an eye on the load factor here. Okay? In other words, while your table is getting bigger and bigger and bigger, at some point you have to make a decision, I need to expand this table. Okay? I need to expand it. Because otherwise you'll get to a point where your program either crashes or stalls. Not good. Okay? Remember what load factor is, and this is really all I'm going to mention about this one is the number of keys divided by the number of buckets. In an open address system, try to keep that number relatively low, like no bigger than 0.8. Okay? I mean, if you're doing linear searching, then you can have it go all the way up to the limit. At that case, you've checked it. Once you get to a situation where you've checked all of them, then you know it's full, and that's fine. But in general, try to keep it around 0.8 so that the hash function will eventually find an empty bucket. If it doesn't find an empty bucket, or if it gets bigger than 0.8, then you have to do this expand thing. Okay. How do we actually do that? So this is the tricky part. All right. It was easy to expand dynamic arrays. Okay. You take the dynamic array, you make it bigger, you copy all the elements in, you've got a bigger dynamic array. It was a little bit harder to expand a circular queue. Remember how we had to do that for a lab? The circular queue one where you had to worry about the fact that you've got a front and a back, and you've got to know which one's where, and you have to copy the right elements in the right location so that your circular nature doesn't break, right, when you're trying to pull elements out. Well, what problem do we have if we just decided to increase the table size of the hash function and made it twice as big? So for instance, if we have the hash function here, right, and it's got a bunch of keys in it, okay, and when we have, and let's say these are the keys, and then they also have data associated with them as well, right? When we hash A originally, right, it's going to go there, and we hash B, it ends up going there, and whatever, right? Well, if we wanted to make the hash table bigger, first of all, what do we do to this? This is the hash function. What do we also say we have to do this to make sure that it fits in the table? The one big thing we had to do for this one. Yeah. You have to mod it, right? So in this case, you're going to have some modulus function, 1, 2, 3, 4, 5, right? And that will actually put it there. OK, put it in the right place. If you double the table size, let's say, there we go. If you double the table size, and you copied all those elements over, you're going to have to change your hash function here to be mod 10 instead of mod 5, right? And what does that do to the hash, most of the hashes in here? What? You can't find them anymore, right? Because remember, the biggest thing about a hash table is that it is deterministic. Your hash function has to be deterministic. It has to put the value in the same place every time. And if you've gone and changed your table size, well, next time hash of A might end up here, or it might end up here, or it might end up here, it might end up in a completely different location, and you'd never be able to find it again. Not so good. What are the solutions to that? How do you think you'd have to expand this hash table, which you don't have to do in the lab today? What do you think, Ian?
We can do it like a circular queue. After you expanded the array, you need to shift the element accordingly, so that after you change the mod, you can still find it.
Well, would that work? Let's say, would just shifting them work? It's a good idea. Would just shifting them actually work in this case? A happens to hash to here. It's like C happens to hash to here, right? So C ends up here in the first one, right? If we're hashing C, right? C hashes to this location right here. Why, by doing a modulus 10, is it all of a sudden going to still hash by some like fixed value? Because two values could, like 0, 1, 2, 3, 4. So 2 and 0, 1, 2, 3, 4, 5, 6, 7. Anything that comes out 2 or 7 both end up there, right? When you do a bigger mod, does that mean that the mod is going to end up in the same location again? Like it doesn't, right? In this case, right, 2 would end up there, and 7 would be 2, 3, 4, 5, 6, 7. So the next value might end up here, right? And in that case, you're not going to necessarily, just shifting doesn't quite do it for you. Good idea. Good idea. Vivek, what do you think?
Because when you create a new array, you're not just expanding, you have a whole separate one. Can't you just rehash all the stuff that you have?
Yeah, can't you just rehash everything? Yeah, so this is one of the issues about this, right? So when your load gets too big and there we go, and you're now doing this, instead of copying the values directly in, just rehash them. If you have the keys, which you should, rehash the key, and then A may end up here, and B may end up here, and C, and then D, and then E, right? And X or whatever, right? You've now rehashed everybody, and then now your function will work. What's the problem with that? Well, it's ON. Either way, you're going to have an ON behavior in terms of the expanding the array. You're going to have to look through all the elements to copy them at the very least. But when you rehash them, even if your hash function is does anything that's moderately hard or slow, well, that's going to slow your whole thing down, right? And if you have 1 billion elements and you have to rehash all 1 billion of them, not such a great idea, right? There are some ways to get beyond this. Okay, so we know we can't do this. So you rehash all the keys, and there is another solution, and this other solution is called consistent hashing, which has the benefits of being able to say that it's pretty much doing what if you do expand the table, your hash function does try to put most of the values in the same place, right? And if you have a consistent hash function that does that, then you'll be OK, regardless of this modulus thing. Maybe you don't use a modulus explicitly until right at the end or something, or you take it into consideration somehow. Consistent hashing is not that easy to do, although some file systems do that when they store hashes for their file system. You can create a hash function that does that. Not the easiest thing to do. And again, it would probably be more advanced and take more time on the average to do that. So it's a solution, but it's not necessarily the best solution. The easiest solution and the most widely used one is when the table gets too big, just rehash everybody. This is one of the issues with some programming languages. Not an issue, but You guys, anybody in here Java programmers? Maybe done some Java? Yeah, okay, a couple people have done Java programmers, or Java programs. Java and C++ share a lot of different ideologies, right? And one of the things that we haven't really gotten into too much, although next week we'll probably do a little lesson on templates. There are whole libraries of functions, like the string function, for instance, that's built for you, basically, right? And when you don't have quite as much control, right? Like there's a hash table function in Java. And when you don't necessarily have as much control, if you're adding to a hash table, Java makes this decision. Now, you may be able to adjust it using certain parameters, but Java makes this decision that when the hash table gets to 0.8 for its load factor, it will just stop what it's doing and rehash all your values into a bigger table. And that can take some time, right? And so for certain types of programs where time, like running time, is important, that becomes a different issue. Like it becomes an issue for how to do that, and you may not have control over it. So it's a little it's a kind of a necessary thing you have to do, this rehashing business. But some languages, like they just kind of their data structure does it for you, and you don't have control over it. And that's what some people kind of don't like so much. Okay, there's a whole other like class you could take on other ideas of this, like not necessarily having control over when things happen. Do you guys know about garbage collection at all? Garbage collection is, in some languages, when you delete items, or not when you delete them, when you stop using a certain variable, right, or a certain object. Well, in C++, we have to delete those. Like that's the idea, right? We have to go and say, hey, we're not using this anymore, delete it. Some languages say, yeah, you don't worry about that. I'll delete it for you. I'll figure out when you stop using that variable, and then I'll go ahead and delete that. And it's called garbage collection, and it makes it very nice that you don't have to do all these, remember where all your deletes and news are, and worry about that. But you don't have control over when that happens. And so sometimes your program can be chugging along, and then all of a sudden it just like slows way down. Well, it could be because this garbage collection is happening. There's a whole field of like how to do garbage collection. In fact, there's some researchers here at Tufts, some graduate students in particular, who do garbage collection and try to make them better make better algorithms that don't slow your programs down as much. Okay, so it's interesting idea, but the point here is you have to rehash these in general, and it takes time. Okay. All right. Other questions on hashing and the open addressing scheme? No? OK. We haven't talked about this yet. So removing an element in a chained hash table, removing an element is easy, or a key is easy, right? A key and a value. You go, you find the key, and then you just do the remove on the linked list, and you're done. If there aren't any elements there, it ends up becoming null, and it's easy to do. In an open addressing scheme, here's the issue. So let's say we wanted to delete this key. Okay? And then we want to go, like, let's say we just make it red and empty in this, which is what we're doing here. Why might that break searching for some other keys? Yeah? You'll think there's no more keys. So let's do this, right? So let's say we make this one red, which means this one's empty now. I guess I should have pointed an arrow over here. This is empty as well. And we go and search for key 3. And remember, keys 2 and 3, 1, 2, and 3, all originally hashed to this bucket. OK, so then you go and you search for key 3, right? And you go, oh, OK, key 3 hashes to this bucket. I'm looking for it, right? This one's empty. Must mean it's not there. Uh-oh. Right? Original hash isn't there. It's not there. And you never actually get to do your little search through because your search has stopped. Ideas on how we could solve that? Yeah, Ben?
Can you mark it somehow so that
Yeah, you mark it somehow, right? So it's pretty easy. You just say, hey, look, this one's deleted. And now we know when we get there, we check first if it's deleted, if there's a deleted marker there, and then we keep going along. So you do have to know that it's deleted. And the other issue is you can never go back to empty again unless you rehash the whole table, right? Because the way that the only way we ever got to key 3 was by finding keys, a key here, and a key here, OK? So that becomes a little bit of an issue. However, right, you may not be able to ever get back to empty, but could you just put another value here? Sure, the next time something hashes into here, don't make it deleted anymore. Put a value there. The other ones will get found, right? Just like normal. You're going to have your same key, your same open addressing scheme to do that, whatever it is, linear, quadratic, or double hashing or whatever, right? And so you'll still find it. So that's what you want to do. You search for key 3. You find that it's deleted spot. And you say, oh, I'm going to find it. I'm going to look next. And I'm going to look next. And we find it. OK, so whew, gotten rid of that deleting part. OK. Sometimes this is also called lazy deletion, which is similar to the lazy deletion we had before for binary search trees. The difference here is that you can replace it. Like it's not like it's. I guess you probably could in a binary search tree too, but in this case, you're going to want to next time just replace it. Or you could also just say, hey, I found a deleted one. I'm going to look for this key. While I'm in the middle of looking for this key, just move it back to the other location. Either the next time do it, or do it while you're looking for another key. But you can do this some sort of management. It's just about managing the space at that point. Knowing that you have to keep some sort of deleted thing so you can find everybody else, and then moving them back or adding a new key in that location when it becomes necessary. OK, yeah. Ben.
If you're looking for key 2, value key 2,
Yep.
and then you move it back, do you have to mark something in the place where key 2 lies?
Well, good point. Do you have to mark something in the place where key 2 lies? Why would you have to do that?
Because then if you move it and it's empty,
This one would be empty now, right?
well, I'm saying if
Yeah.
you moved key 2 back,
If you moved key 2 back. Oh, yeah, if you moved key 2 back, yeah, in that case, if there's still other keys that would rely on it later on, how do you figure that out? Good question. You would probably mark this one as deleted and then move it back here. Because what you're trying to avoid, in this whole thing, what you're trying to avoid is having to do too many jumps, right? The more jumps you have to do, the slower your table is going to be, right? So anytime you know that, look, my keys will end up here on the first go around, well then, if we get to one, mark this one as deleted and move it here. And then you'll be able to say, save a little time the next time that happens. OK? And again, this stuff has been, there's lots of research that's gone into what are some good hashes to use to make sure that these schemes work. And sometimes you could, you could end up foiling your plan at some point. Like you could move this to here, but maybe this one doesn't get it hashed as much as, or maybe this one gets hashed more than this one. And it's bottom line, you probably want to do some empirical testing and look at some research on it before you actually build, something for real. For the stuff we're doing, not a big deal. But if you're going to build a hash table that you're going to use at Facebook or Google or something, right? Well, then you need to really know what you're talking about and start picking a good hash function and justify it. Yeah, good. All right, other questions on this? Great. OK, so then, like here, you could mark that empty, or you could mark it deleted, depending on if you know it's the last one. All right, so is there a perfect hash function? In other words, is there a hash function that will not create any collisions? And it turns out that for arbitrary data, no. If you don't know the keys ahead of time, you can't find a perfect hash function, except in very trivial cases where you know the entire spectrum of your keys. Like remember the two-letter words we were talking about? When you have two-letter words and you know that you only have two-letter words and they're all lowercase letters, you know that there's 676 total words, and you can come up with a perfect hash function, which was the one we came up with, right? It says hash it to this bucket, there will never be a collision, and we just have to limit ourselves to these keys. That's relatively straightforward. But otherwise, if you don't know the whole range of keys ahead of time and you don't actually know the keys in general, then you can't come up with them. If you do this perfect hash function that doesn't collide. If you do, though, OK, you can come up with a perfect hash function. It is not trivial, right? There are various programs that you can actually look at that will find a perfect hash function, but they're not perfect. Or they're not trivial, and they're not so easy to do. Lots of interesting papers on that. I was doing some searching on it, and I found a ton of interesting papers. There's one that's located here that actually refers to a whole bunch of other methods. And it says, here's a method for coming up with a perfect hash function. Then you have to go through this big algorithm to do it. And that can take some time. But again, if you know that you're going to have the keys ahead of time, why not? Then you don't have to worry about collision schemes. So it's the only case where you're not going to have to worry about the collision schemes. If you happen to have a collision function that actually uses exactly the number of buckets as the number of keys, we not only call that a perfect hash function, we call it a minimal perfect hash function, which sounds kind of funny that you're actually adding another adjectives to the actual perfect hash function. But that's what we're doing, right? It's called a minimum one. The one we did for the 2-letter words was a minimum one. And there are other ways of doing this. So there's some blog posts on this and other places you can look and see if you can find those minimum, or you can build those minimum hash functions. Minimal perfect hash functions. Okay, but those are the only. It's not trivial, and I won't actually test you on trying to come up with one of those. Okay? But again, it's dependent completely on if you know all the keys to begin with. Okay. All right. So that was about it for the main hashing discussion. I thought it might be interesting to go into some other types of hashing here. Okay. There is this whole field called cryptographic hashing. And it's actually pretty cool, right? Cryptography in general is kind of neat. When I was in the Navy, well, I still do some of this stuff in the Navy. Unfortunately, when you get high enough in any job, unfortunately, and they put you in management positions, all the people that work for you do the fun stuff. And you get to manage and push a lot of paper, and I don't like that stuff at all. But anyway, cryptography and cryptographic hashing here is something that's, it actually, in many cases, the World Wide Web runs on this sort of stuff. Okay, you couldn't really have security without these ideas. Okay, so it's kind of neat stuff and important. This little hash right here. Okay, that's I say little. It's actually not that little. I think this is actually 224 bits long. Okay, whatever 224 divided by 8 is, that'll give you the number of bytes it is, characters it is, right? It's 50-something characters or something, right? What that is you can take an arbitrary string, okay, and you can hash it to this value, okay? And anyone know what this came from? Of course you don't. That's the whole point, right? The point is that actually comes from struggle bus, which is a word I learned recently in lab, okay? And because I'm talking to some of you guys, and you tell me your projects are a struggle bus, right? But anyway, and then I found this kind of neat little GIF, so I had to put it on here. Anyway, so what the struggle bus is how you would actually go backwards from this key to get the word or the phrase struggle bus, right? You're not going to be able to do it, and that's kind of the whole point of this. Cryptographic hash functions, we really need to be what we call one way. Okay, and by one way we mean you can get the hash, but you can't go back from the hash back to the original string. Okay, and not necessarily true for all hash functions. Right? If you look at that perfect hash we had before, if you know that you have word at 422, you can go backwards and figure out what the word should have been, right? But in this case, we don't want to do that. Okay? Why? Digital security. Okay? Our cryptographic hash functions are a hash function that takes an arbitrary length of data, okay, and then does this whole algorithm on the whole data and comes up with one somewhat long, in some cases, string or number, such that any change in the data will actually change the hash function. And we'll get into some of the details about why these are important in a minute too. Okay, so if you can't read this here, but this is a little Python one-liner that you could do to get this to go from the message into this thing we call a digest, okay, which is really the hash of the function. Okay, that's what the digest is called. And what you do is you can run this little thing, and it performs a little algorithm. Tough to see on the board, but it's in the notes. And it comes out with this hash here. Okay, and that's called the digest. It's called the hash, and there's lots of ways we use that in a cryptographic or in a digital security sense. Okay. So here's the 4 big things about cryptographic hashing. Okay, you want to make sure your cryptographic hash meets the following conditions. Okay, and we'll go through each one of these individually. All right, first of all, it's easy to hash the value for every given message. Okay, in other words, you're not going to want it to be hard. Okay. Infeasible to generate a message that has a given hash. We'll get to why that's important. We want it to be infeasible to modify a message without changing the hash. Those of you who are writing this down, I'm going to go through these individually in 1 sec. But I just wanted to blast them up here to begin with. And then finally, you don't want 2 different messages to have the same hash. We'll see why that's important too. Okay? And we'll start to think about ideas of why this stuff becomes important in a digital security fashion. Okay? All right, first one was it's easy to compute a hash value. Why? Well, look, if you're going to be doing a lot of these hashes, you want it to be fast. In general, we'll talk about why we might not want that to be the case in a bit. But you want it to be fast to also be able to verify messages. Okay? We'll talk about why that's the case too. A lot of times, cryptographic hashing is used to say, is this message really A, from the person I think it is, and B, like based on the data I think it's from? Okay? And that's a verification process, which we'll talk about in a minute in a little more detail. Okay? It's kind of cool. So you want it to be fast, generally. Not all the time, but generally. Okay? All right. An ideal cryptographic hash function, it is infeasible to generate a message that has a given hash. In other words, you don't want to have a hash and then say, I think this other function will hash to it. Okay? And then you've got lots of collisions. You don't want it to be collisions. Okay? You also don't want this to be like for passwords. And I used this example in class the other day. Right? Rose has a password that gives her some hash. Right? And then David comes along with a different password. And if they have the same hash, that means David can use his password to log in as Rose, even though it's a completely different password. You don't want that kind of collision. Do collisions happen? They do. You try to make them unlikely. Okay? But you try to make them relatively unlikely. The other idea is you don't want them to be, you don't want to be able to go backwards from a hash. Right? You want them to be this one-way thing so that you can't take the hash and figure out what the password was. That would be bad news too. Okay? The other idea is this idea of deception. Okay? If we're going to give another example in a second about how you can use hashing to verify things, right? But what you don't want to do is you don't want to have a hash that supposedly came from some data, and all of a sudden somebody has different data that they produce the same hash from, because then you can't verify that it's the right one. Okay? It gets into a little bit of detail about how deception can work, but this verification is really important. We'll get to that in another second or two. Okay, so you don't want to be able to generate a message that has a given hash unless you know what it should be to begin with. Okay, like the password, something like that. Infeasible to modify a message without changing the hash. This, I think I gave this example the other day too. Okay, Rose has a password that's hello, right? David has a password that's HELL0 because he's being clever, right? And putting the little, like replacing zeros with like the letters that or the numbers with kind of the equivalent letters, right? You don't want those two to be even close to the same hash. Why? Because then you might be able to use one. If you know David's password, you might say, oh, this hash looks like a different hash that's in this set of hashes I have, and I'm going to try other variations of it and try to get to it, right? So struggle bus happens to hash to this value, right? Struggle bub, right? One letter different. Look, there's like no letters that are the same in there. I mean, there's a couple every so often, but that's kind of a random artifact here, right? Out of 54 letters, some are going to be the same. But the idea is you can't change one letter and get a hash that looks anything like the original. Okay, and that's an important part of cryptographic hashing, this kind of random nature of the output hash. Okay. All right, and then finally, you don't want to have two messages with the same hash. This goes back to the idea of you don't want two people's passwords to go and produce the same hash if you're doing a password. You don't want to often find that many passwords that collide. They are going to, or hashes that collide. It's going to happen. That's the way it goes, but you want to minimize that. There's algorithms to minimize that. Okay, so here's some examples. Now, in cryptography, we always use two characters. This is just kind of tradition. Some people did this when they first started talking about cryptography. We use two people, one called Alice and one called Bob. Okay, you can use various ideas of what your Alices and Bobs look to you, but we're going to talk about Alice and Bob here in terms of some of these ideas of why cryptographic hashing is important. So let's say, and this is definitely a made-up kind of example because it's kind of silly, but let's say that Alice says, I've solved this really hard math problem, right? And Bob says, hey, I want to solve that math problem too, but I also want to make sure you solved it. to begin with. Like, and Alice says, hey, I want to make sure that you know I'm the first one to solve this. Okay, and then you can think of various ideas where this might not be so perfect. Like, for instance, let's say that this can be used in law fairly frequently, right? If you hash a message that has like a date in it or something, and you want to know that it came from the person that said it, then you can hash it, and you'll be able to tell that it came from that person. Another example might be, let's say you're doing some sort of scientific research, and you want to prove that you came up with it first. If you produce a hash and then publish that hash, everybody knows when you did it. Then you can use it to see that you're the one who first came up with this, but you don't have to tell everybody else the answer. Although in science, we generally try to like tell everybody what our solutions were so people can check them. But if it was a math problem, and let's say Alice wants to tell Bob, hey, I've solved this first, and then Bob says, okay, well, I'm going to try to solve it on my own, but I want to prove that Alice is the one who did it. Alice will write down her solution and then hash it, and then give that hash to Bob and say, here's my solution, but it's hashed. And I'm not telling you what the key is for it, or what the password is, or whatever. Okay? So when Bob actually solves the problem, then Alice says, here's my hash, or here's the actual how I made this hash. Go ahead and check it. Right? And Bob produces the hash of the solution, checks it against the hash that she originally gave him, and says, oh, okay, you did come up with the original solution. Okay? So that's how you can use this to verify that someone had produced something previously. Kind of neat. Okay? And you don't actually get the answer. I mean, Alice could go, here's my answer, just don't look at it. Well, Bob says, oh, I always peek at things like that. Well, in this case, he doesn't need to. He can have the hash and have no idea where it came from until she gives him the how to figure out the hash, the key or the password for that hash. Okay? All right. Here's another example, and I've talked about this one before as well. Password verification. You don't want the people who run your web forums or Google or the people at the tech guys here at the CS department or in the school to know your password. Okay? For a lot of reasons. Number one, it means they won't be able to log in with you. But also, people generally use passwords, the same passwords for different systems. I happen to actually kind of have my own little very simple hash when I make passwords up, right? I have my password that's like part of my password, and then I have this like function that's based on, say, the website name or something. And it's really simple. It's like, I don't know, it's like the first, third, and fifth character of the website name or something, right? And then I put some other little string in there that's always the same and whatever. And I try to kind of basically hash my passwords so that they are so that I can remember what they are, but then nobody can, if you figure out my Google password, you won't also be able to log on to my Reddit account or something like that, right? Because, I'd rather you send emails than like post on my Reddit account. But send emails as me. But the point is that you can use this to, what you do is you just hash somebody's password and then store that hash with the person's username. And the next time the person logs on, you have them hash the password again and then check the username, check the hash against the hash. And if they're the same, then you know that it's that person, to the approximation that it could be a collision. But the odds are slim that there's going to be a collision. Okay? So you just match the hashes. Okay? All right. So in that case, is there a case where hashing should be slow? And I mentioned this about 3 times now, and the question is there one? I probably wouldn't have asked it if there's not. But why would you want to have a hash be slow? Any ideas? Yeah, Abhi.
With security reasons, so say someone has access to the algorithm,
Uh-huh.
they would probably do like thousands of tests at a time.
Ah, OK. Thousands of tests at a time. Yeah, you want to keep it slow. Is that what you're going to say too? Back there? Yeah. So the idea here is absolutely that. If you want to have a password hash, right? If I have a really fast computer and I can check lots and lots of passwords, right? Well, the faster I can check those passwords, the more of them that I can get through, and the more chance that I have of figuring out the hash to your password. Because remember, what you have to do to figure out the hash is find a password that will hash to that value. Okay? So absolutely. Bob goes and steals a set of usernames and hashes. This happens relatively frequently, right? Unfortunately. Security being the way it is, it's not that hard necessarily to steal a set of password or a set of usernames and hashes, unfortunately. Okay? Most good hash functions are public. In other words, if you're using a Unix system, okay, you can go look up how to do the hash on all of your users' passwords. Now, why is that a good idea, and why might somebody say that's a bad idea? Ideas why you want to publish your hash functions?
People approve them.
So people can what?
Improve them.
People can improve them. That's one reason. What's another good reason? Anybody ever hear of the NSA? Right? It's been in the news a lot in the last couple of years, right? For not necessarily good things. The NSA, and I don't know any details about this, but at least none that I'm going to tell you. At least none that I'm going to tell you. No, I don't know any details. But let's say the NSA or like some other group that's equally as big and robust and wants to find like secrets and things. If the NSA could somehow build a little what we call a backdoor into your password hashing function, then they would be able to use some other method to get the hash of your password than your password, which is not so good. And forget about the NSA for a sec. You don't actually want the people who run your regular old systems to have some backdoor password thing. Okay? The idea is if you and that's the first thing. The second thing is you do want them to be improved. Not only do you want them to be improved, but you want them to be checked, right? If you come up with a hash function that you say is this great cryptographic hash function, but I'm not going to tell you what it is, right? Who's going to know that it's a good hash function except you, and who says that you're going to necessarily be able to determine that? If you open it up to everybody else being able to check that, then they can run through all these different checks and see if it collides and see if, make all these checks on it and find out if you have a good hash function. So most are known. Okay? So Bob, if he's got a fast computer, can go and start hashing all of these passwords, and he's going to pick the easy ones. Like he's going to pick password, and he's going to pick like I love my cat, right? And whatever, right? And he's going to pick all these like great easy to do passwords, which you shouldn't have, by the way, which like 1, 2, 3, 4. Like that's a huge password people use, right? That's easy to hash, right? And Bob's going to go and hash these, and then he's going to create this table. Okay, we generally call that a rainbow table, and what it is he comes up with this table, and then he can figure out what all the hashes are, and then log in as you and get your credit card information, all that kind of baloney that he wants to do. All right. If, however, you've got a slow hashing algorithm that even though Bob has a really fast computer, it's still going to take him a while to create these hashes, then you start to slow down Bob's ability to get your password hash, or link your password to the hash. Okay? What do you do this? You call it key stretching. Okay? Key stretching is just saying increase the amount of time it takes. Unfortunately, computers are outpacing some of these key stretching algorithms. In other words, the speed of computers outstretches them, and computers get faster than the slowdown based on the hashing function. That's not good, right? We call stretching methods that are based on just the time as CPU bound. In other words, the faster your CPU is, the faster the faster your hash will come out. There's also some ideas on making your hash memory bound, which means, hey, take a lot of memory to do this hash. And then even if you've got a really fast computer, unless you've increased the amount of memory to some amount that's huge, you're not going to be able to do lots and lots of them fast. It breaks caches, it breaks other things that make you faster to do that. So the whole idea is just because you've got a fast CPU doesn't mean you're going to be able to get these. Or a fast GPU. GPUs are used for these hashing things a lot these days. Okay? So that's when you want your password hashing to be slow. You generally don't want it to be, but in this case you would. Questions on that? Okay. Another way to actually combat this whole rainbow table business is, okay, so Rose uses her hello password, right? All right, now that might not be quite as clever as some other passwords, right? Could be hello, I love my cat named Scruffy, right? But that's a better password. It's longer, it's got more letters, right? But let's say she uses hello. Well, if I'm a smart Bob, I'm a smart hacker or whatever, I might already have a hash table built that will take hello and put it into, and have the hash for that. What we do instead is we say, all right, instead of just hashing the password, let's hash the password plus Rose's username, right? And now you've got this hash like this. So Rose picks her password, and then you also pick the username. Do that. Now it's not just the password. It's the password plus the username, which means that everybody who uses the password hello is going to have a completely different hash. Okay? So both Ben and Rose use hello. Well, Ben's hash is going to be different than Rose's hash because it's based on his username, and hers is based on her username. So it's another way to combat this idea of, oh, go ahead and have all these hashes in this table already. You have to redo the whole hash table for an individual person. So it's good. Okay? All right. Here's another example. File verification. Yeah, question. Marcus.
So does it necessarily, the salting phrase, does it have to be different? Let's say you add like Bob to all the hello.
Right.
Like if they don't know the phrase, but it's still at the
Ah, sure. So yeah. OK, so good question. Does it matter if you always add the same salt on there? Well, what do you think? If I can, you have to somehow store the salt. Like you have to store that other thing you're going to add, right? And if I steal your passwords and your hash function, and I happen to steal what you're storing that one salt, I still need to do one giant table for everybody's password, right? Because then, but if it's different for every individual user, then you only have to do it once, or you have to do it. Sorry, you have to do it once for every person. Good idea, though. Okay. All right. Here's another example. You download a lot of stuff from the internet, right? Sometimes, especially if you're downloading from somewhat nefarious places, like say Pirate Bay or whatever, right? There's like places you can download from where you don't necessarily trust what you're downloading, right? Well, what you do is you actually publish the hash. The person who created that file publishes the hash. Now you have to be able to trust that person, and that's different, or that entity, and that's a whole other part of the equation. But the idea is, once you download a function, you can write a little, you can create or do the hash of that. Once you download that file, you do the hash on that file and compare it to the hash that's been published, and you'll know that the file itself has not been changed. If you change one character, the whole hash should change. So if the file is exactly right, the hash that you compute on your own computer at home should match the one that somebody else did remotely, and you'll be able to verify that the file exists. You can actually do that. In fact, Linux has a little MD5 function which will create a hash for you. MD5 is not a very good one these days. It's too short. It's been broken. You can actually Google the hash and come up with a password. I mean, it's not the best, but it will at least allow you to figure out if you've got a secure system there, or if you've got the same file that you think you do. Okay. Here's another one, digital signatures. Yeah, sorry, go ahead. How do you hash a file? It's exactly like anything else. You've got it's a fixed string, right? And that string, you could go character by character through it, and then do your hash function. Now, your hash function hopefully is your hash function hopefully has the ability to take in as much data as you want, and then that's how it works. So it just walks through all the characters and does some function on all, or groups of characters, or blocks of characters, or there's a lot. Go look up cryptographic hash functions. You'll find zillions of different ideas. But I've gone and tried to look at some of these sometimes, and they do take some like mental power to like get through how it's working. But that's because they're kind of advanced. How do you know an email came from the person that said that it's sent from, right? You could look at the headers and all that, but those can easily be spoofed. What can't be spoofed is if you have what we call, this is a whole other topic in general. We're not actually going to get a chance to do much of it, but public and private keys. You can actually hash a message to someone, and then that someone can take what's called your public key, rehash that function or that message, and get an answer that's actually your private key. Oh, no, sorry, it's not your private. It's the message itself, meaning that you actually can guarantee that as long as you trust the person who sent you the public key to begin with, you can guarantee that it came from that person. Okay? Which means that you can guarantee that someone sent an email, and it's all about digital signatures, which is kind of cool because in today's world, you can actually sign something digitally, send it to someone else, and they can prove that it came from you, as long as they trust the people the bigger part of the system. It's kind of difficult. Okay? This is how it actually works. I'm not going to read through that, but basically you can prove, again, you prove that your message came from the person that sent you the message was the person that actually did, not some person in the middle who spoofed it. Okay? Public key cryptography, Huge other topic. Maybe we'll spend some time on it in a future lesson, but it's kind of a cool, really neat thing. And by the way, the whole web is based on public and private key encryption, right? When you go to Amazon, right? Amazon talks to your computer using these methods. Okay. All right. Questions on that? Awesome. We'll see you guys in lab or on Wednesday, and there's also some references here.